Hello everyone and welcome. With this video, I'm hoping to cover a bit of the items related to the preliminary sizing of elements as they're covered in your textbook. And this is going to relate to reinforced concrete elements. So this is information that you will find in Appendix B of your textbook, the latest edition of your textbook, as well as chapter 22 of your textbook. So hopefully this would be a help to you. One thing that I'm going to remind you of or let you know is that I'm going to put timestamps on this video because it's going to be a slightly longer video than what you're used to from me, because I'm not going to break it up. I'm going to go all in one shot. And that way you can read in the description of this video on YouTube what each timestamp refers to, so you can go to it rather than just have to wait for the whole video to play. Okay, without further ado, let's do this. The first thing I'd like to chat about is rebar. So what I've reproduced here for you is what rebar designation looks like in Canada. In your textbook, you get designation that is used in the US. It's American designation, but this is the metric designation that it's used in Canada. And the way that it's usually set up is that there is a number followed by the letter M. So this would be read as a 10M bar, then 15M, 20M, 35M, and so on and so forth. And that number before the M refers to the approximate diameter of that bar. So you can see in millimeters. So you can see that the diameter, say, of a 10M bar is 11.3 millimeters. And then in this column, I included the area, the cross-sectional area of that bar. So the reason I'm bringing this up is because I want you to notice something that's very important as it relates to construction materials. We're going to compare 10M bar with a 20M bar. A 10M bar has a diameter of 11.3 millimeters. A 20M bar has a diameter of 19.5 millimeters. So that's almost 1.7 times bigger. The 20M bar, that is. Okay? But look at what happens when you compare the area of these two bars. It's almost 3 times larger. Pardon me, check that. It's exactly 3 times larger. What does that mean? Well, in our business, in construction and civil engineering, material is sold by weight. So if something is 3 times as large area-wise, even volume-wise, that means it's 3 times as heavy. That means it's 3 times as expensive. So that's important to recognize. So look at that. Increasing the diameter by 1.7 increases the cost by 3 times when it comes to rebar. But that's true for any material that is sold by weight. So for example then, let's compare 10M bar against maybe 30M bar. Okay? So you'll notice that the diameter of a 30M bar is approximately 2.6 times the diameter of a 10M bar. But look at what happens to the area. It's 7 times larger than the area of a 10M bar. So that means that getting something that's 2.6 times bigger results in 7 times the cost. Okay, so this is important to point out. I wanted to make sure that you saw this, right? 7 times more expensive. Okay, all right. In terms of the first rule of thumb that I want to play around with, I'm going to talk about control joints. And this is covered in the lecture that this refers to in more detail. Control joints are those saw cuts that are typically put into slabs, concrete slabs. And as it shows in your textbook, the approximate width of a saw cut, of a control joint, is 3.175 millimeters. So that's, I believe, approximately 1/8 of an inch. The rule of thumb, in terms of how deep this control joint needs to be, shows right here. 0.25 times the thickness of the slab, as shown right here. So in this case, if we assume that we have a slab that's 375 millimeters, 375 millimeters, not meters thick, in order to find then how deep the cut has to go, we need to do 0.25 times 375 millimeters, and we get 93.75 millimeters. So then, is that how deep that cut is into the slab? No, no. What we do typically, and it will depend on whatever company you work for, but for the purposes of this course, this is what we're going to do. We're going to round up to the nearest 5 millimeters. So what we're going to get as an answer is actually 95 millimeters. Okay? So that's going to be the depth of the control joint according to this rule of thumb. Now, another thing that I want to point out is right here, that's where the rebar is showing. And I want to just remind you that the distance between the rebar and the closest concrete surface is referred to as concrete cover. It's covered in more detail, pun intended, in the lecture, okay, for topic 3. But I want to point out that you should know about this, and that a good place to bookmark in your textbook is table 22.1, and this is based on the latest edition of the textbook, chapter 22. Okay, but this is the rule of thumb for the depth of control joints in concrete slabs. Okay, so now that we know how to do the depth of control joints, how about spacing of control joints? So in this case here, what I'm referring to is, can we calculate what the east-west spacing needs to be in a slab and the north-south spacing needs to be for control joints, assuming this is the plan view right here of a concrete slab? Okay, so the rule of thumb, as it shows in your textbook, which is exactly where I got this from, is that the distance, the maximum distance for the cuts, the control joints between each other, is 24 times the thickness, as long as it's no more than 4.572 meters. So if you remember from the slab that we just looked at, the thickness was 375 millimeters. So if we calculate the maximum distance, as 24 times the thickness, where the thickness is 375 millimeters as given to you, 2 out of 3 times when I did this calculation, I got 9,000 millimeters. So check to see if you get the same answer. Now, is that then what the spacing is going to be for the control joints? No, because you'll notice that it is more than 4,572 millimeters. Right? This requirement right here. So that means that upper limit, 4.572 meters, becomes the largest spacing that you can have. So what we would do then is take the total length and total width of the slab and figure out based on that how many spacings are allowed. So in this case, we're going to assume it's given to you that the length and the width of the slab are the same at 19.812 meters. So then what I would do would be to divide the length by this spacing that I obtained. So that'd be, I'm going to do this all in millimeters, 19,812 millimeters, and I'd divide that by 4,572 millimeters, which comes from here. Okay. Now this number here would change if this had been smaller than 4,572. Okay, that's what we would have gotten, but it isn't, so we have to live with that. Okay, so this number is going to tell us how many spacings we're going to get at 4,572 millimeters. So when I divide one number by the other, I get 4.333 spacings. So we're done? No, because you can't use 4.33 spacings, and you want to make anything related to construction and measurements Francesco proof, right? So what you do is you round it up to 5 spacings, a whole even number, right? You cannot round it down. It's 5 spacings, and then you simply reduce the spacing so that 5 fits an equal number of times into the length or the width. So all you're going to do then is repeat 19,812 millimeters, divide by 5 spacings, and that's going to tell you that you're going to be using 3,962 millimeter spacings. So that's going to be your actual distance north-south and east-west in this reinforced concrete slab for your control joints. Now, obviously, this would change depending on the length and the width of the slab for your particular slab, but this is the way you would do it. The next rule of thumb we're going to work with is figuring out the slab thickness for flat plate slabs and flat slabs. This is taken straight out of Appendix B of the latest edition of your textbook. There's more information related to this in the video, the main lecture video related to topic 3. Okay? But we're just dealing with rules of thumb. So what we're going to be doing is, if we assume, we're going to start with flat slabs first. If we assume that the spacing between columns, so that's the grid line spacing, if you will, is 5.639 meters, then the rule of thumb says that you have to divide that span by 30. Okay, and that's what the span is referred to in this case. It's the distance between columns. Typically the clear distance, but in this case it works. So I'm going to do everything in millimeters because it's more convenient for me. So 5,639 millimeters divided by 30. The nice thing about these rules of thumb is whatever unit you use here is going to be the same unit as your answer right here. So millimeters, millimeters. So when I divide 5,639 by 30, I get it then a thickness of slab that is 187.97 millimeters. Great. So is that the thickness of my slab? No, right? You don't want to forget. Then you want to round this up to the nearest 5 millimeters if it's not a proper whole number. So in this case, then that becomes 190 millimeter thick slab. That's simple. Okay. So now let's repeat this, but let's do it for a flat slab type construction. We're going to assume a spacing that's been given to you of 7,010 millimeters or 7.01 meters. The rule of thumb in this case, I'll do it in blue, is going to be the span divided by 35. So that means that you're allowed to get a slightly thinner slab. So then 7,010 millimeters, right? Remember that with these rules of thumb, whatever unit we use here is going to be the same unit we get for our answer. So 7,010 millimeters divided by 35. What does that give me? I think 2 out of 3 times I get 200.29 millimeters. So is our slab 200 millimeters? No. We have to round up always the nearest 5 millimeters for the purposes of our course. So in our case, the answer is going to be 205 millimeters. Make sense? You're awesome. Let's move on to the next. So, let's go back to this for a second. One thing that I want to point out that you can see here for flat slabs is that flat slabs are different from flat plate in that we actually have drop panels, right? Where the columns connect to the slab. And that's what we're going to be working on for the next rule of thumb. Drop panels. I took this image with all the rules of thumb present in it from your textbook. go to our lecture for topic 3. It's one of the videos. It has exactly where I got this from. It's in your textbook, chapter 22, I believe, of the latest edition. But what we're going to be looking at is calculating the dimensions, the plane dimensions, length and width of the drop panel, as well as the thickness of the drop panel. Okay? In this case, we're going to use the same dimensions as we had in the previous view, so that the spacing between columns is 7.01 meters or 7,010 millimeters. The slab thickness, which we found previously, is 205 millimeters. So we're being asked to find the panel width, which is also the same as the length, because you want it to be the same size typically, and then the panel thickness. That's what we're looking for. So let's start with then the thickness. The rule of thumb for the thickness, as it shows right here, and again, I took this straight from your textbook, is that the thickness of your drop panel is equal to 0.25 times the thickness of the slab. In our case, we were given that the thickness of the slab was given to us as 205, or as we found, we calculated it. So 0.25 times 205 millimeters, I get 51.25 millimeters. So is that the thickness of our drop panel? No, don't forget, we have to round up to the nearest 5 millimeters. So that would mean that it would be 55 millimeters, right? Great. Now let's elevate it to one more step. Typically, simple drop panels are formed, as shown here, using dimension lumber. So usually then the depth of the drop panel is to match then the depth, more or less, of a piece of dimension lumber that is used in this case. So if you really wanted to step it up, and that's not what I'm asking you to do, say, for the purposes of a test or a final exam, but what you would do is you would find the piece of dimension lumber that has the closest dimensions to this, that are bigger, right? They can't be smaller than 55 millimeters. And what I found was that a 2x3, a nominal 2x3, actually fit the bill. And that's because a 2x3 in real metric units is, 38 millimeters by, 38, I have it right here, by 64 millimeters, where 38 is the width, the full width, and 64 millimeters is the full depth. So in fact, you would make this drop panel then actually 64 millimeters. Okay? But for the purposes of this course, tests, final exams, this is the acceptable answers. Okay? Okay, so now that we found the depth, I'm just gonna write it right here. 55 millimeters, right? That's gonna be the thickness. The next thing we're gonna find is gonna be the drop panel width. And the way that's done is by using this rule of thumb right here, which says that half of the width of a drop panel is equal to the column spacing divided by 4. The column spacing for us, divided by 6. The column spacing for us is given right here. So 7,010 millimeters. Now you can do it in meters too if you want, but I like millimeters better because it makes more sense than when it comes to calculating these rules of thumb, because that's going to be the same unit I get here. But you can do it in meters as long as you remember that then the result is going to be in meters. So best 2 out of 3 times, 7,010 millimeters divided by 6 equals to 1168.33 millimeters. That's the half width. So is that the answer? No. Don't forget, we have to round up by 5, the nearest 5 millimeters. So that means that the half width is 1170 millimeters. But because this is the half width, as is shown right here in your textbook in the rule of thumb, we actually have to multiply this by 2 to to get the full width, which is going to be 2,340 millimeters. Okay, so overall then the final answer, the dimension for this draw panel, length times width times thickness, is going to be 2,340 by 2,340 by 55, and all of this is going to be millimeters, right? All of these are millimeters. Make sense? Terrific. Let's move on to the next one then. The next thing we're going to chat about, which is going to be the conclusion then of, or for the second half, I guess, of this, is going to be stuff related to one-way slabs and two-way slabs. I'm showing here an image that I plucked out of your textbook, but is also used in one of the lectures for topic 3. Go check it out, please, because I'm just going to remind you about the difference between one-way slabs and two-way slabs, and it all has to do with the ratio of the long span by the short span of that slab. Okay, so let's say for this here that's indicated as a one-way slab, this would be the long span, and then this here would be the short span of the slab. Okay, they're the plane dimensions. Okay, so in our case, let's say if we had a slab that had a long dimension of whatever and a short dimension, the width of whatever, if that number is greater than 2, then that is considered a one-way slab. If that number is less than 2, then that slab is considered a two-way slab. That's important because the rules of thumb that we're going to cover now, that are also shown in Appendix B of your textbook, are based specifically on being able to identify whether you're using a one-way slab or a two-way slab. Some apply only to one-way slabs, some apply only to two-way slabs. Let's do this. The first rule of thumb we're going to do and look at is going to be for figuring out the depth of... Sorry, let me just clean that up a little bit. For figuring out the depth and width of a girder beam, the depth and width of a beam, and the depth and width of a slab for a one-way solid slab. Now, just to be clear, I'm indicating these secondary structural elements in red as the beams, these primary structural elements in blue as the girders, and then the slab is the portion of the concrete that's sitting onto all of that. Now, one thing that needs to be figured out is that in terms of the beams, you're showing a whole bunch of intermediate beams here, right? I'm counting 4, but I don't want to get in the whole spacing of beams. So how about we look at something more like this, where I've removed all the interior beams, and the beams are going to be shown here along the perimeter, and the girders are going to be the perpendicular direction here along the perimeter. Okay, so that's what we're going to do. My recommendation for calculating the dimensions for slabs and beams and girders supporting these one-way slabs is first to figure out if this is in fact a one-way slab. We've been given a length and a width of the slab, so in order to figure out if it's a one-way slab, we have to do the ratio between the length and the width. So I'm going to do this in millimeters again. If I do 9,754 millimeters, like this, and I divide that by 4,572 millimeters, like this, what do I get? When I do best 2 out of 3, I get 2.13. That's greater than 2, so that confirms that it is in fact a one-way slab. Which means we can use the rules of thumb that are shown on your screen right now, which I plucked straight out of Appendix B of your textbook. Go check it out. So my recommendation is when it comes to usually using these rules of thumb, start with the slab thickness first. And in this case, the slab thickness is a span divided by 24. But what is this span? Well, the span, according to the rules of thumb for one-way slabs like this, the span is the clear distance between beams. Okay? And the way that it works in this case, it's the short direction because we're looking basically the distance between beams here. Okay? And beams are always oriented, if they're the secondary structural elements, in the long direction, right? The larger of the perpendicular grid spacings, because you want many beams but only few girders. So the spacing is actually going to be the shorter one of the two, in our case W, if you have beams like this. So W, if you remember, is 4,572 millimeters. I'm going to do this in millimeters because then it gives me a thickness in millimeters right here. So if I do 4,572 divided by 24, best 2 out of 3, I got 190.5 millimeters. Is that the thickness of our slab? No, don't forget it needs to be round up to the nearest 5 millimeter for the purposes of our course. So we get 195 millimeters for the thickness of the slab. I'm just going to park it here so that I have the freedom to erase some of this information right here. Okay, so let me clean things up a little bit and then we'll come back to do the beam. Welcome back. Now that we've cleaned things up and we've figured out what the thickness of the slab is, we're going to move on to working with the beam right here. Okay, so we want to work first with the span, figuring out the approximate depth of the beam. And the rule of thumb, as it shows here, is it's equal to the span divided by 15. Now here's the interesting thing about the span of a beam. The span of a beam is always parallel to the long direction of the grid lines, right? Because you want many beams but only few girders. So the span is going to be this dimension here based on the grid line spacing we've had for this. So 9,754. So it's going to be, in this case, length divided by 15. So that's going to be 9,754 millimeters divided by 15. And whatever units I use here are going to be the units I get in terms of the depth of my beam right here. So 9,754 divided by 15, 2 out of 3 times, I obtain 650.27 millimeters. And when we round up to the nearest 5 millimeters, that's 655 millimeters. Okay. Now, something that's important that I want to point out right now is this. Based on these rules of thumb, what I'm doing is I'm just sketching a section right through here for this beam and slab. Okay, so you can see our beam here and you can see our slab. This depth of 655, it is inclusive of the thickness of the slab right here. Okay, 195 right there. So that's important. Okay, so 655 is not the depth below the slab, it's the whole depth as I've shown it here. The next thing we're going to do with this rule of thumb is figure out the width of this beam. The rule of thumb for that is that it's 60% of the depth, or 0.6 times the depth. So we have the depth here. If we multiply that by 0.6, we get a depth. What did I get? 393 millimeters. So we round that up to the nearest 5 millimeters. That gives us 395 millimeters. Make sense? Awesome. Okay. So now that we have the depth and width of the beam, I'm going to clean things up a little bit and then come back so that we can do the girder. Terrific. So now that we're back, we're going to do now the dimensions of the girder. I'm going to do this in red, just so we can differentiate from everything else done so far. We're going to do the girder with its rules of thumb here. So the rule of thumb for girder in a one-way slab is span divided by 12. So the span of the girder goes in this direction, which typically is the short direction, because you want your girders to be shorter than your beams. So the shorter direction is this one right here. So the approximate depth of a girder in this case is going to be W divided by 12, where W in our case for this specific example is 4,572 millimeters, or you can do it in meters if you prefer, divided by 12. And best 2 out of 3 times was 381 millimeters. And then round that up to the nearest 5 millimeters, that comes about to be 385 millimeters. Now look at this, okay? The depth of the girder, right? This generally vertical dimension of the girder is actually less than the dimension of your beam, the depth of your beam. And you can't have that, right? Your girder cannot be less deep than your beam. At the very least, it must be at least the same depth of your beam. So here's the interesting thing. The depth of the girder then needs to be bumped up to match the depth of the beam, like this. Okay? So depth of the girder, in this case, needs to be bumped up to match the depth of the beam. So now the girder gets bumped up, so it too must have a depth of 655 millimeters. And a reminder that this depth, again, is inclusive of the thickness of the slab. We don't have to recalculate the width of the girder because the rule of thumb is the same, 0.6 times the depth, and we already calculated it that. So now we know that the width of the girder is 395 millimeters because this is exactly the same amount that was calculated for the beam. Okay? So that's for one-way slabs with beams and girders all around it. The next thing we're going to do is play around with two-way slabs. So let's say we have a two-way slab here with these dimensions, right? The width and length of the slab, which basically kind of match the grid line dimensions. Now, to properly know whether or not we can use these rules of thumb, we have to first figure out whether or not it is in fact a two-way slab. So we're going to do the long dimension divided by the short dimension, and we're going to see what that gives us. So 6,706 millimeters divided by 4,572 millimeters. That gives us, what do I get? Best 2 out of 3. Let's see if I can find it. 1.47. Which is really good for us, right? Because it's less than 2. And it tells us that it is, in fact, a two-way slab. So now that we have confirmation it's a two-way slab, it means we can use the rules of thumb that are shown here. So we're going to start first with the slab itself. So we're going to do first the slab thickness. And again, I got these rules of thumb from Appendix B in the back of your textbook, latest edition. The rule of thumb for the thickness of the slab is the span divided by 36. Excuse me. What is the span? We have the choice between two amounts here. Easy for two-way slabs. Always pick the largest one because it'll give you the thickest slab. So in this case, it's 6,706 millimeters, right? The larger one of the two right here. And when I do this calculation, best 2 out of 3, what do I get? 186.28. So that's the thickness of the slab, right? Wrong. You want to make sure that you always bump up, round up to the nearest 5 millimeter. So in this case, 190 millimeters. Okay, so now we have the thickness of the slab. I'm just going to reproduce it right here, 190 millimeter. Lovely. Okay, so now I'm going to clean this up a little bit and come back. Actually, you know what? I don't have to clean it up. I'm going to do in red the calculations for the beam using these rules of thumb that I found right here, again, Appendix B. So the depth of the beam, which again, remember, it's inclusive of the thickness of the slab, is equal to the span divided by 15. And what is the value of the span? Again, for two-way slabs, super easy. Always pick the larger one of these two, okay, of the dimensions of your slab. So in our case, it's going to be 6,706 millimeters. That's equal to, what do I get? Best 2 out of 3, it's 447.07 millimeters. Rounded to the nearest 5 millimeters, that's 450 millimeters. And again, remember that this vertical dimension is inclusive of the thickness of the slab. So just to be clear, I'm going to sketch it here. If this were, say, the section I were looking at right here, this is what the beam would look like, if you pardon my poor sketch. So this vertical dimension right here, from top of slab to bottom of beam, 450 millimeters, is inclusive of the thickness of the slab here, which is 190 millimeters. Okay? The only thing that's left to do now for the beam is to calculate the width for it. And the rule of thumb, you see it right here, it's same as the ones that we did for one-way slab, 0.6 times the depth. The depth here is 450. We multiply that by 0.6, and that gives us, what do we get? 270 millimeters. Spot on. Okay, so this beam is 450 millimeters deep by 270 millimeters wide. Great. We've done this. So this is true then for both the beam, all the beams along the perimeter of the slab, if it's so set up. The one thing we did not do is actually look at the columns supporting each one of these, right? We've so far just looked at beams and slab thicknesses. So that's what we're going to do then with the next thing. We're going to look at figuring out the dimensions for reinforced concrete columns if they're supporting one-way slabs or two-way slabs. So in this specific case, I'm just going to make it clear here. We have a one-way slab, okay, and we've played around with this same slab previously, so we confirmed that it was one-way slab based on these dimensions. The rule of thumb for columns is that, first of all, it's a good idea to ensure that they're rectangular, kind of like what's shown here. So that means that the length of the column and the width of the column must be the same, okay? The other beautiful thing about columns is that columns don't care if they're supporting one-way slab or two-way slabs, because for columns, it's all about tributary area. Okay? So as long as we can figure out the tributary area of the column we're looking at, we're good. So let's look at this specific case. We're being asked to look at the ground floor column, sizing it, assuming that it supports 3 stories above it. And again, I want to be clear, this is going to be an interior column, not a perimeter column, okay? So that means that it's got neighbors, columns on either side northwest, either side east-south. So in this case then, we recognize that for interior columns, the tributary area is based on the grid line spacing. Okay, so it is going to be 9,754 millimeters by 4,572 millimeters. Now you can do this in millimeters or you can do this in meters. I'm going to keep it in millimeters so that I keep it the same throughout, and the answer is in millimeters for these dimensions. Okay, so when I multiply the grid line spacings in perpendicular directions, I get a tributary area of 44 million, because I'm doing this in millimeters, 44,595,288 millimeters squared. Okay, now this is the area of ceiling, if you will, that one interior column is supporting on the ground floor. However, what we have here is that this is 3 stories that we have to figure out. The ground floor is supporting 2 more stories. So we have to take this and multiply it by the number of stories to make sure we account for the fact that that bottommost column on the ground floor is also supporting everything above it for however many number of floors are above it. So when you multiply this by 3 stories, we get 133,785,864 millimeters squared. Like this. Okay, that's the total tributary area that a ground floor column, an interior column, is supporting for the 3 stories above it. Now, the rule of thumb that's shown in Appendix B of your textbook gives weird numbers for interior columns because it's using imperial units, right? Square feet. When you actually use metric units, this is what you're going to be using. If you're going to use low or regular strength concrete, you're going to divide this by 1,404, not 10, as it shows in the back of the book. If instead you're going to use high strength concrete for your columns, then you're going to divide this tributary area by 2,808, not 20, as it shows in the back of your book in Appendix B for concrete columns. So let's do this one first. Let's assume that we're going to do this column using low strength concrete. So we want to take this total tributary area for all 3 stories and divide it by 1404. Okay, so 133,785,864 millimeters squared divided by 1,404. Okay, when I do that best 2 out of 3, what do I get? I get 95,289.08 millimeters squared. Okay. Now, what I got with this area right here is the expected area of our square column. The area of this shape right here. Now here's the nice thing, because this is a square, the area of a square is length times width. And because the length and the width are the same, it's like saying length times length, or length square. So if we want to find then what the length is, like this, we just do the square root of the area. That's it. So all we're going to do to find the length is just do the square root of this area right here. Right? This number right here. Now I'm running out of space, so I'm going to just write it in the top right corner. When I do the square root of that number, best 2 out of 3 times, the square root of that number gives me 308 0.69 millimeters. So that means that's my length and the width of that square column, right? No, don't forget we have to round up to the nearest 5 millimeters. So it becomes 310 millimeters. Now this is going to be the length and the width of the column, assuming again that we're using low strength concrete. You would then repeat this process, keeping the same area, but using instead 2808 if you choose to use high strength column. You can try it out. If you follow the same process, you will get the length and therefore the width of the column is actually going to be 220 millimeters if you do it for high strength concrete. Okay? So then what happens if we're going to figure out the column for a two-way slab? Nothing different, because columns don't care whether it's two-way slab or one-way slab. The only thing columns care about is tributary area. That's it. So in this case, we have a two-way slab. We've used these same grid line dimensions previously, so it can be confirmed that it is in fact a two-way slab. But all we have to do now is make sure that we're looking at the correct thing. We're being asked to figure out the column dimensions for the ground floor column, interior column, that's supporting 4 stories above it. So we would go through the same process again, figure out the tributary area for 1 story, which comes from here, multiply that by 4, and then either divide by 1404 or 2808. So let's do that together. So we want to figure out the tributary area that's based on these grid line dimensions for an interior column. So if we do 6,706 millimeters divided by 4,572 millimeters, best 2 out of 3, what did I get? I get 30 million, if I'm looking at this correctly, 659,832 millimeters squared. That's 1 story worth. Because we're looking at 4 stories, we have to take this and multiply it by 4, right? Because that's how much the ground floor column is supporting all the way above it. So when we do that, the total tributary area being supported is actually 122,639,328 millimeters squared. Like this. And then we have to decide, are we going to be using low strength concrete or regular strength concrete to do this? If so, then we have to take that area and divide by 1,404. If we're using high strength concrete, then we take that area and divide it by 2,808. In this case, let's assume we're going to use high strength concrete. So we take that big number, 122 million, divided by 2808. When we do that, we get this number, 43,674.98 millimeter squared. Again, it's this number, 122 million, etc., divided by this number here. That is the area of this square column right here. Okay, so because this column has a length of L and a width of W, and L equals to W, right? The way to figure out then what the length and therefore the width is to simply do the square root of that area. And the square root of this area right here equals 208. Oh, no, sorry, not 208. I'm just going to fix this a little bit. Just like that. It's actually going to be 208 218. No, I'm making a silly mistake again. I'm not paying attention. Sorry, it was 208. That was correct the first time around. Okay. It's 208. I guess this is what happens when I rush, huh? 208.99 millimeters. Like this. Is that the answer? No, we round up to the nearest 5 millimeters. So that makes it 210 millimeters for both length and width, because we're told this is going to be a square column. Okay? If we repeat this whole process, but instead we use low strength concrete, you can try it yourselves. We get a length and therefore a width, if you follow this same process, of 300 millimeters. And this is the number that you get after you round up to the nearest 5 millimeters, which is what's going to be expected for this course. Okay, the last thing that needs to be discussed is, what if then the column is a circle? Well, how do we figure out the dimensions of a circular column versus a square column? The process is exactly the same. Okay, it's all about tributary area, regardless of whether it is a one-way slab or a two-way slab. Okay, and it's still going to be so that if you're using low strength concrete or regular concrete, you're going to divide whatever area you calculate by 1404. Or if you're going to be using high strength concrete, you're going to be dividing that tributary area you calculate by 2808. The only difference though is that you have to recognize that the area of a circle, right, is not calculated by doing length times width. The area of a circle is pi times the radius squared, or pi times the diameter squared divided by 4. Okay, so once you have the area, then you're either going to solve for the radius or the diameter. Now, because this is not a math course, so that you have to be able to manipulate it, I'm just going to write for you what that would be. So the radius is going to be equal to area of the circle that you would calculate divided by pi, and then the square root of the whole thing. That's how you calculate the area. The diameter is very similar. Okay? It's going to be the 4 times the area divided by pi, and then the square root of that. Now, my math colleagues are going to cringe at the lack of simplification in this, but that's perfectly fine. Okay? It's an engineering course. And that's how you would calculate the radius or the diameter of this. I hope this helps. I hope this was helpful to you. You can watch these videos as many times as you want. Don't forget that there are going to be timestamps at the bottom so that you can simply skip to the item that you're interested in. Thank you so much for your time, and have a lovely day.